Hello, I'm Gilles, lead graphics programmer at Arkane. Today I'll present an overview of the rendering technologies in Deathloop and how Luke Rammer and other people at AMD helped us to reach better image quality and better performance on both PC and consoles. She will present after my talk some specific optimization we did for AMD hardware and how we integrated together some AMD technologies into our game. A few words about me. I've worked in the video game industry for the past 20 years, on console and PC projects, on various engines, both commercial and developed in-house. I'm lead graphics programmer at Arkane since Dishonored 2, and on all Arkane games developed with the Void engine. The latest one is Deathloop, released last September. I really hope you all played it. What will I talk about? I'll first introduce the Void engine and how it evolved over the years, supporting more and more platforms and APIs. Then, we'll go through the main improvements we implemented for Deathloop. We'll finally look at how we implemented ray tracing in an engine which was not really suited for it in the first place. After Dishonored 1, we had to choose on which engine we would develop Dishonored 2. We settled on id Tech 5, which was developed by id Software, another ZeniMax studio like Arkane. We liked how the engine was designed, and we knew that if we needed help we would have it. And near the end of Dishonored 2, we had a lot of help from them. Over the years, we rewrote a big part of the engine, and not only on the graphics side. The gameplay code was also entirely rewritten from scratch, plus we integrated many middlewares for audio, for physics, UI. Let's begin with Void Engine Graphics API usage. When we got id Tech 5, it was DX9 and OpenGL. And one thing to note is that like several other engines, the executable for internal builds contains both the editor and the game code. It allows level designers to test their levels directly from the editor. We labeled the Void Engine version used to ship Dishonored 2 as 1.0. On Xbox One, we needed to use DX11, and we also switched the PC version to DX11 to avoid maintaining two different APIs. For Deathloop, the API choice was more difficult. The game started as a fully multi-platform project, not only PS5 and PC. As you can see, we went from 7 platforms to only 2. But it was done in a few stages. For a few months, we kept maintaining the previous generation versions before the decision was made that we would be next-gen only. It removed a couple platforms. Then, a great news for us, the Sony exclusivity deal was signed, and we were able to drop support for 3 more platforms, each using their own API. Obviously, having only 2 platforms and 2 APIs to support was a big relief, especially during the final debugging and optimization phase, which, as you all know, can be quite painful. The DX12 version needed a lot of work to run well, especially in editor mode, as its graphics resources management system is very different from the game. Artists and designers keep adding and changing stuff all the time, and we couldn't pre-bake that data as DX12 likes it to be. So we had to implement specific systems to avoid too many dynamic resources creation. We also hit a few DX12 SDK bugs, shader compiler bugs, driver bugs. This led us to even think about shipping the DX11 version alongside the DX12 one. In the end, all those bugs were fixed, and we finally felt confident we could switch the entire dev team on our DX12 editor and only ship this version to players. Let's now look at what we changed for Deathloop besides the graphics API. First of all, before everything else, we chose to switch from forward to deferred rendering. I'll talk more about this in a few minutes, as it was quite an important decision. When we started development on Dishonored 2, PBR rendering was still new, and there was no standard BRDF to implement. But we chose the wrong one. We chose the Ward BRDF while everyone else used JJX. For Deathloop, we decided to move to JJX, which had become the standard and was the default BRDF in the authoring tool we used. We also added HDR support, which is common these days. ACES tone mapping gave us better results than our previous filmic tone mapper, but it came with one drawback. The computation can't be inverted with full precision. We had to rely on an approximation for the reverse function, but it was good enough for our needs. On previous generation consoles, we had tried to implement particle lighting using a few different options. Unfortunately, none of them was acceptable either in terms of quality or in terms of performance. Our artists needed to adapt every environment effect to the local lighting condition, which took them a lot of time and effort. They didn't want to relieve it for Deathloop. We implemented Doom 2016 decoupled particle lighting to finally have lit particles for Deathloop. Even with this feature, we noticed early on that when we had a lot of effects on screen, in 4K, the dynamic resolution code had to lower the resolution by a pretty big factor to compensate the fill rate hit, and the image quality took a big hit too. So we also decoupled the particle rendering resolution for the main view resolution, and we now have two different dynamic resolution usages. Particle resolution can go down to 64 times less pixels rendered. The loss of resolution is not very visible on particles until we really reach low resolution. Whatever the amount of particles we have on screen, we keep a fixed quality for the opaque geometry, which is far better overall. We had an order-independent transparency solution in place since Dishonored 2, based on an accumulation and opacity buffer. It was not perfect, especially with additive blending modes, but it was quite cheap and gave good results. We were able to adapt it to have two sets of inputs, one in full resolution and one in lower resolution, so we could keep some specific effects in full resolution and sort all of them together during the OIT pass. All the transparent surfaces in the environment can also stay in full resolution and be sorted correctly. As they are not animated like particles, the loss of resolution was a lot too visible. They also had some junction issues with the opaque geometry around them. Here, the screenshots demonstrate this case. The small full resolution transparent surface you can see is the glass covering the spotlight, with an opaque metal case around it. So we kept it full resolution in order to avoid junction issues. The art direction depended a lot on efficient decal rendering, so we had to completely rework our decal system. We took inspiration from Doom's decal management code to implement something better suited to our deferred renderer. Here, you can see what the game would look like without any decals. The buildings lose most of their paint layer. On Dishonored 2, decals had their own diffuse map, normal map, and roughness map, and only blended themselves over the previous geometry, computing lighting one more time per overlapping decal. On Deathloop, decals are rendered into their own G-buffer, which is read during the main geometry G-buffer pass. Depending on per pixel decal G-buffer values, they can blend one or more of the material-based textures with the geometry ones. We can, for example, have decals which only modify the underlying normal to only add scratches on surfaces. Like many other games, we have two types of decals. Static decals are manually placed by level artists. Their geometry is generated in the level editor from box projections they set up. They are not projected at runtime. Artists can pick which static geometry they will be displayed on, making possible to exclude windows or neighbor objects where they don't want this decal to be spilled. Static decal Z order can also be tweaked by artists to make sure they overlap correctly. Dynamic decals, on the other hand, are spawned at runtime, and we have a lot less control over them as they are projected at runtime as well. It is quite easy to always display dynamic decals over static ones, but in Deathloop, we have one additional specific issue: the snow. Because we have a lot of snow in Deathloop. On the left, you can see a work-in-progress version of a map portion. On the right, several static snow meshes have been reworked and added, but you can also see snow on the pile of garbage and a thin snow layer on the left barrels and on the roofs. While not dynamic at runtime, this kind of snow layer is a procedural part of the base material. The issue with this snow layer is that it has to cover static decals. However, if we drop a grenade near the barrels, we need the dynamic explosion decal to cover the snow. So we need to store the decal type. We could have stored this information in the decal gbuffer, but it was not the best performance-wise. It would have been necessary to read a full decal gbuffer 32 bits pixel to determine if there was a decal present and its type. So instead, we chose to store this information in stencil bits. Obviously, Pix is not displaying stencil with those colors, but red shades were not nice in a PowerPoint. Blue pixels are covered with static decals, red pixels are covered with dynamic decals, and green parts are covered with both types of decals. We need to know when the two types of decals are present, because in the absence of snow, or if the snow is not completely opaque, they could be both partially visible and blended together. So here is a sample gbuffer shader. So we start by reading the stencil. If a decal is present, we read the decal gbuffer. If the snow is not fully opaque, we apply the static decal. We are able not to do that if the snow is fully opaque, because the static decal is not visible in this case. Then we can apply the snow over the static decal. And we finally apply the dynamic decal over the snow. In all this presentation, I talk about snow, because we first designed this feature for the snow, but artists also use this feature to add dust layers on some objects. This can be useful for a lot more than just snow. Having per pixel normals available in the gbuffer allowed us to add an SSR pass in addition to our prop-based reflections. Prop reflections were only able to handle static reflections and were also suffering from pretty low resolution. As you can see on this screenshot with SSR, reflective surfaces are now much better integrated in the overall image. We improved a few more features to have a better overall image quality, and we even added ray-traced ambient occlusion and ray-traced shadows on platforms supporting it. On the ambient occlusion side, Cacao provides a good improvement over our old custom AO, which was targeting performance, not quality. It is also very scalable. We were able to expose 3 different quality levels. Dishonored 2's image was often too soft and blurry. We improved our temporal AES shader, but it was not enough. We added a real sharpening option, and it helped a lot with this issue. AMD CAS is used with native resolution rendering and also when using DLSS. RCAS is used in both FSR modes. So why did we switch to deferred rendering? During Dishonored 2 development, especially for post-processes, we often missed access to some data which could have been readily available with a gbuffer, for example normals. our forward shader was already really heavy in terms of VGPRs and bandwidth usage. Outputting a normal buffer was not really possible. Its complexity also made it difficult to optimize. Switching to a deferred renderer helped with a lot of those issues, and also allowed us to use a lot more async compute passes, as most of the lighting was done in compute shaders instead of pixel shaders. With access to a normal buffer, generating rays in our ray tracing code was also a lot easier than it would have been without it. We eventually managed to get our deferred renderer to offer better performances than our previous forward renderer, which was of course one of the goals. Here are a few screenshots of some of our debugging tools. We have obviously standard views to display the raw gbuffer content, but we also have more advanced ones like a texel ratio or a vertex density view. For the texel ratio, users are even able to choose for which source texture they want to visualize it, albedo, normal, or everything really. All those views helped a lot the artists to check when they respect the constraints given to them and to debug material issues more easily. So what about ray tracing? We managed to add ray tracing functionalities to Deathloop, and I now explain how we succeeded. When we started development on Deathloop, ray tracing was still new, and not many games were taking advantage of it. We had long had the desire to try ray tracing, but we couldn't afford to spend too much time on it, because it was a big feature that was available only for a tiny percentage of PC players. What decided us was mostly the fact that the new generation of consoles supported it. Wider support on PC was also announced, but not yet available. As we were developing a PS5 exclusive, it made sense to try and reach a better image quality. How did we start? Obviously, before even trying to cast a ray, we needed to generate acceleration structures. For our first PC-only prototype, we only supported the static environment geometry and, more importantly, only fully opaque geometry without any alpha test. It allowed us to avoid writing the code to refit and rebit classes and the class, and also to avoid the need for any texture management. We started by rendering the main scene with ray tracing, without any texture, with an ortho camera. And we got our fantastic first ray traced image. Impressive, isn't it? A scene made of a single quad, viewed from above, but at least it was working. The second image we got was a little more meaningful. It was the same scene, but viewed from the player camera. Sorry, I couldn't find any screenshot of this step, so we can skip it and go directly to step 3. It was time to check our acceleration structures would support a full game level. But with all pixels the same color, the image was not very useful. So in this step we also added flat shading, using the vertex normals, interpolated using the barycentric coordinates provided by the DXR API. After this step, the next logical one became, let's render this scene with its albedo textures. And we hit our engine main limitation for this kind of features. It is not a bindless renderer. We did not have access to all the textures. We still managed to hack it quickly, but it was not viable for real usage. At that point, we decided that ray traced reflections were out of reach for this project. Maybe the next one? Two ray tracing features were still achievable: AO and shadows. Here is our first screenshot of 1 ray per pixels of shadows. And the obvious conclusion: we needed a good denoiser. So we spent a lot of time testing many denoisers. None offered good enough quality to ship our game with it. The main issue was often the ghosting. We asked around if anyone knew a good denoiser, and AMD offered us to test Fidelity Effects denoiser, which was not yet released at that time. The first prerequisite we had was met. It was open source, and we were allowed to use it on consoles. So we implemented it, and the results were really good. It only officially supported shadows, but worked like a charm for AO2. The lack of support for reflections was not a problem for us, as we were not doing reflections. I learned that the latest version of this denoiser now supports reflections, but we haven't tried it yet. Regarding the console, just know that the stock AMD version still had to be adapted somewhat to fully work on console. Way32 and Way64 mode is automatically chosen by the driver on PC, but it's not on console, and wave intrinsics are not exactly the same. As we were satisfied with the results we had so far, we had to implement the last features without which we couldn't ship a ray-traced game. I won't cover the console port here, but I'll just say that the APIs are different enough that we had to write two almost completely different low-level code paths. We still managed to keep the high-level code similar enough to ease maintenance. Moving objects were very easy to handle. We just had to update the TLS. Skinned meshes were a little trickier. For performance reasons, we had already implemented a skinning compute shader to pre-skin all the needed meshes at the beginning of the frame. We then used them during the remaining of the frame as if they're static meshes. It turned out to be exactly what we needed. We only had to refit the blasses each frame with the updated geometry. Alpha test was a lot more difficult to support correctly, mostly because the renderer was still not bindless. We had to collect all the needed textures each frame, and add their descriptors in an unbuffered resource heap. We also had to maintain an indirection table in order to reference them from the ray tracing data. On PC, texture streaming was easy to support, as we can sample from MIPMAP 0, which has the best resolution available. It was more complicated on consoles, but it was also due to the lack of bindless resources. The final step we couldn't avoid was optimization. As soon as we enabled ray trace, the frame rate tanked for multiple reasons. We had a lot of CPU side code to manage the BILAS and TLS updates, as it had to handle load switches in addition to animations. We were able to multithread it quite easily. AO is very costly. More costly than shadows for the same ray count because of ray direction divergence. GPUs never like divergent stuff, and ray directions is not an exception. So, we added an option to compute AO in half resolution. It was also a big performance win. BILAS and TLS updates were good candidates for async, as they use a lot of ALUs, but are not very hungry in terms of memory bandwidth. Dispatch race shaders don't use the same hardware units as regular shaders, or not as intensively. We were able to launch them on async pipes in parallel to other GPU work, and it was also a huge gain. It was a huge gain we expected to have on GPUs known to have dedicated ray tracing hardware units, but it was also a huge gain on all vendors' GPUs. As a final word, I'd like to thank AMD for their support. It's been a pleasure working with them. And Lou will now tell you more about the exciting features we're still adding into Deathloop together. Bye!
Hi, and thanks to Gilles for covering the first part of this presentation. I will cover now the second part. And yeah, I'm Lou. I'm a GPU developer technology engineer at AMD, and for the past few months or even years, I worked together with Arkane Lyon on Deathloop. And we've done several optimizations and also feature integrations to this game. And in my talk, I will cover 2 optimizations we've done and 1 feature integration. And you may already guess which feature integration it is, because we released a teaser about it not too long ago. And yes, it is about integrating FidelityFX Super Resolution 2.0. But first, let's talk about optimizations. And I picked 2 topics for this talk because I think they're interesting also for the wider audience, and you probably also can apply some of the takeaways to your titles. So the first one is barriers. It's a bit more high level. I will talk about barriers in general and our performance recommendations, and also how to analyze barriers and how to use our tools. And yeah, I will conclude this topic with a short example from Deathloop. And then the second talk will be about basically a 1-line shader change, and that we've done, and we achieved some great speed up with just this minor change. And usually these type of optimizations are what developers love, because this change didn't had any effect on the visual output. But yeah, first let's talk about barriers. And barriers, they're not a new topic. We've been talking about them basically since the introduction of DirectX 12 and Vulkan, and we are still talking about them. And the reason is quite simple, because barriers can have a high impact on performance. They can drain the GPU, they can prevent passes to overlap. But if you don't have the correct barriers, if you place them wrong, then you can have severe stability and also correctness issues. So when you first implement barriers, you of course want to make sure that they are correct, so that the game runs and that the game looks correct. Because if the game doesn't even launch, there's nothing to optimize for. So this is always the first step. But this also means when we start looking at optimizations, usually there's a lot of room when it comes to barriers. And in the case of Deathloop, this was also true. The general performance recommendations, they haven't changed, to be honest, basically since we started talking about them. Maybe some minor details, they can change depending from the architecture or also from the driver maybe even. But the general performance recommendations, they did not change. Yeah, they're still true, and they will be still true probably for a while. So it is minimize the number of barriers used per frame, batch groups of barriers into a single call, and also avoid general common layouts unless required. So minimize the number of barriers used per frame. I mean, this is very broad in general. Sometimes it's difficult to achieve and also difficult to spot, because you kind of need to know if this barrier is really needed, if you could place it differently, or maybe even you could configure your passes differently. So yeah, this is very general. But the second point is quite easy to spot. For example, when you use RGP. RGP is our Radeon GPU profiler tool. It's a frame analyzer, and it basically lets you see all the commands that got submitted to the GPU. So you see also all the resource barrier calls, and you see them, you see if they're basically back to back at each other, or if there are other calls in between. So what you don't want to see is something in the screenshot. You have dozens of resource barrier calls just back to back and nothing is in between. So you usually want to have one resource barrier calls which contains all your barriers that you want to submit at this point of doing your frame. And then you want to have some other call, for example, dispatch call or draw call. Yeah, so this is quite easy to spot. And yeah, if you batch them, you reduce the overhead, but also you make it easier for the driver to do some optimizations. Some optimizations are simply not safe to do if the barriers are not batched. For example, removing redundant operations. So you can have even a bigger benefit from batching the barriers than just getting rid of some overhead. Then the other point is avoiding general and common layout transitions, unless required, because sometimes you need them, of course. So in RGB, you don't see the specific transitions. You can see them using pix or render, for example. What you do see is what this barrier causes. Like, because sometimes barriers, they're not necessarily let the GPU wait. I mean, most of the time they do, but not always. But they also have some other effects than just letting the GPU wait for work to be completed. They also invalidate caches. They can flush caches. They can also cause decompressions. And these decompressions, you can spot them using RGB. And if you see them, I would highly recommend to double check if your layout transitions, if they're really as optimal as they could be. So how to spot them in RGB? You go to the overview panel, then select barriers, and then you get a list of all the barriers that got submitted during this frame. And then you can also order them depending on the different attributes. So by default, they're ordered by, I think, submission time. But here in this screenshot, I ordered them first for FMAS decompression and then DCC decompression. And this is, again, quite an extreme example, because here we have a couple of FMAS decompression and a couple of DCC decompressions, and ideally you want none of them. I mean, as I said, sometimes you need them. In this case, none of them were actually needed. So by optimizing the layout transitions, we were able to get rid of all of them. But yeah, if you see these in your game, just double check if they're really needed. Then you also see other things. So for example, the cache invalidation flashes. So this barrier that I marked here, it's quite a common barrier. It's not really an expensive barrier. It just synchronizes between the shader stages and invalidates the local caches. So if one dispatch writes to an output resource and the next dispatch reads from this output resource, the invalidation of the local caches just makes sure that the second dispatch reads the correct values, so that it reads from a global cache, because this global cache is visible to all compute units, and you know it contains this, like, the correct data. So this is what this barrier is for, and why these local caches get invalidated. But sometimes it's not enough. Sometimes we also need to invalidate the L2 cache, the column dev buffer backend, sorry. And yeah, and it depends on the next possible command. So basically, the driver cannot see into the future. So depending on the barrier, how it's configured, it has to account to, okay, which command is possible according to the configuration, and then I have the barriers to play safe. Barriers in Deathloop. Deathloop uses a conservative automatic barrier generation system. It's very robust, so it generates all the needed transitions, and it's also super convenient because developers, they don't have to think about the barriers, they don't have to think about the transitions that are needed. Everything is handled automatically. However, since it's quite conservative, sometimes unnecessary barriers are issued. So everything will be correct, so the output will look correct, there will be no crashes caused by barriers, but the performance might not be always as optimal as possible. So sometimes what happened is that barriers got issued that just transition the resource into a state back and forth. So conceptually, what happened, something like in this diagram, so we had a dispatch, but we had two dispatches. They're reading from the same resource and they're writing to the same resource. So potentially they could overlap, but they couldn't because this automatic barrier generation system inserted barriers in between and just transitioning the input texture to a write state and then immediately back to the read state. And these two barriers in the middle, they could simply be removed. And then the two dispatches were able to overlap again. So something like this happened in the compute skinning buffer sparse, and it was quite extreme. So there were barriers around every dispatch call. Even if the next dispatch was not dependent on the previous work, the barriers just caused the buffers to switch state back and forth, and you ended up having 100 to 200 barriers per frame in this function. So they solved this issue by adding a manual barrier management code path. So they just went in and basically just, okay, in this case, the automatic barrier generation system doesn't work really well, so we do it manually. And you can see a before and after pix capture. So see in the before one, we have a lot of barriers between the dispatches. Some batching was done, but the batching logic, this did not succeed all the time, as you can see. And yeah, so manually this got all like improved, and now we have like dispatches actually be able to overlap. And this is the just the two RGB captures before and after. And here you also can nicely see how the dispatches overlapped. And yeah, this change improved the performance of this particular function of up to 60%. Yeah, so depending on where you are in your development timeline for the game, it might be worth to do it manually, because changing the automatic system has quite some risks involved. Of course, it's the preferred way, but it might be not as simple. And yeah, that's why sometimes it makes sense to actually do it manually for specific passes. Okay, moving on. Enough about barriers. Now I want to quickly cover this one shader line change that we did. And this change affected how the output was written to the UAV target. And the particular shader that was involved is the scattering light fog shader. So the scattering light fog shader, as the name suggests, computes the light that gets scattered by fog. So you can see that in the screenshot. It's like this particular look that you get when like this. It's a bit foggy environment, and then you have the light shining through. But this also means that the impact of this shader is very scene dependent. So in scenes with a lot of fog, it was actually quite costly. But in scenes with little or no fog, the shader was not significant at all. It's a lighting shader. It's not too different from the direct lighting shader. So what the direct lighting shader does, it goes through all the lines and then computes the final RGB values and writes it out to its UAV target, which had the format RG11B10 float. And yeah, it just wrote the three values out. And so the output white pattern for the direct lighting shader looked like this. So it was a coalesced 256 byte block. Now the scattering light fog shader, it also computed the RGB output values, but the UAV target had a different format. So for the scattering light fog shader, it actually has 4 channels RGBA 16 float. But the shader was still just writing to 3 channels. So the output white pattern looked like this, and this is not the coalesced 256 byte block anymore, and this goes against our recommendation. Why do we have this recommendation? Because partial whites and compression, they don't go well with each other. If the data is uncompressed, we can simply mask the whites for partial whites, and that's all. But we cannot do this for compressed data. So if we have compressed data, a coalesced 256 byte block needs to be decompressed first, and then we need to compress it again to preserve the untouched channels. That's why if in order to efficiently use compression, you have to fully overwrite the underlying data. So you have to write in coalesced 256 byte blocks, because then we can directly write compressed blocks and we don't have to decompress first to preserve anything, because in this case we don't need to preserve anything. So that's what we did. And also, fortunately, the 4th channel was not even used, so it didn't contain any valid data, so we could just override it with zeros, for example. But yeah, and that's what we've ended up doing. But of course, sometimes this 4th channel may contain valid data. So in this case, what you can actually do is to read this data and then just write it again. And then you should measure the performance, of course, but this can also give you a performance boost. And yeah, so the observed speed of the scattering light fog shader was up to 30%. So the UAV target was actually compressed. we probably would have not seen this performance uplift if the UAV target was uncompressed. Yeah, so in scenes with a lot of fog, this was actually quite significant. So really try to write to UAV targets in compute shaders in core less 256 byte blocks. So the rule of thumb is to have an 8x8 thread group write to 8x8 blocks of pixels and really write to all channels. And if you have to preserve one of the channels, try just reading it and writing it again. And when we tried to do this for this shader, even though it was not needed, we also saw performance uplift of about 30%. But yeah, test, of course. Enough about optimization. So now I want to talk about FidelityFX Super Resolution 2.0. I will talk about the integration specifics to Deathloop. If you want to know about the algorithm, the optimization we've done for this effect, and also general integration guidelines, stay on for the next talk, because the next talk will be a deep dive for FidelityFX Super Resolution 2.0. But yeah, here some screenshots just to see FSR 2.0 in action. So on the left, you see native rendered in 4K with DA and sharpener enabled. Why they are enabled, I will talk a bit about it later. And on the right, you have FidelityFX Super Resolution 2.0 quality mode, so upscaling from 1440p to 4K. And what I want to point out here is this board with the sun on it. And you can really see that the edges, like the wooden pattern, they're really well reconstructed in the upscaled image using FSR 2.0. I'd say even better than compared to native. But yeah, Deathloop is the first title in which we integrated FSR 2.0. You can even say that the integration part was part of the development, because it was an early proof of concept in a real game. As you know, it's always different integrating a technology into a game compared to just into a sample. And yet the feedback and the lessons learned we got from integrating FSR 2.0 into Deathloop directly went back into development of FSR 2.0. It's a temporal upscaler, so we have a few input resources, of course the color buffer, the depth buffer, and the motion vectors. And Deathloop also provides the exposure texture. And the FSR 2.0 comes with its own TIA and also has its own sharpener. Deathloop makes use of the FSR 2.0 library. In the beginning, when there was no library, we used the source code, so we just used the C++ files and compiled it. But as soon as the library was available, we switched to the library. And we are making of the API entry points, context create, store, and dispatch. We don't make use of the helper functions. The reason is because in the beginning there were no helper functions because there was no library. That's why at the time when we had access to these helper functions, we already implemented their own way in Deathloop, so they were simply not needed anymore. So that's the reason, because Deathloop was a bit ahead of the library in this case. And we need to recreate the context when the equation parameter changes. And one example is if the presentation resolution changes. And when this happens, we need to be careful because we cannot destroy the FSR 2.0 context immediately because it might still be in use. So the resources might still be accessed. And Deathloop uses triple buffering. So at the time when we record a frame, another frame is already executed on the GPU and another one is already in the pipe. So that means when we realize, okay, this context needs to be destroyed, we need to add some logic to synchronize. So what we do is we kind of like register the FSR 2.0 context and for destruction, and then we actually destroy it at the end of frame n.2 here, because frame n is executed from n.1 waiting. So the end from frame n.2 we destroy the current FSR 2.0 context. However, we can immediately create a new context. So this also means that for a short time, we have two FSR 2.0 contexts alive, and this is totally fine. Yeah, the FSR 2.0 library can handle several alive contexts. What the library does not for you is doing this synchronization. So the engine is responsible of this, and also the engine is in a much better position to decide when to synchronize and to how. That's the reason. The input, the color buffer is a linear color space, image formats RG11, beta, and float. To improve the precision, the values are multiplied with a pre-exposure value. So FSR 2.0 needs to do this as well. So we pass in this pre-exposure value to the FSR 2.0 per frame parameter. And as I already mentioned, Deathloop provides its own exposure texture, but in principle this is not needed. FSR 2.0 can also compute its own. Motion vectors. Luckily, Deathloop provides motion vectors for nearly all scene elements, including vegetation, and this is great because motion vectors really help to get a high quality upscaled image. So here I have an example screenshot for vegetation. They were actually moving in the wind, so that's why they are not exactly the same, because the brush was a bit moving due to the wind. But you can really see that the quality is quite high, and motion vectors really help with that. For elements that don't have motion vectors, FSR 2.0 will use some other tricks. Output. So as you already noticed, I compare the upscaled image always with native TIA on and sharpening on, because the native rendered image is actually quite soft in Deathloop. So what actually happens is that if you use the quality presets from high to ultra, I think it's high, very high in ultra, the sharpener will be enabled by default to kind of improve this very soft image. And we want to achieve a comparable result with FSR 2.0. So that's why by default we also enable the sharpener. And FSR 2.0 comes with its own sharpener. It's robust contrast adaptive sharpener Arkane. And since it has its own sharpener, we have to disable Deathloop's sharpener to avoid double sharpening. Deathloop supports all four FSR 2.0 quality modes, so quality, balance, performance, and ultra performance, which is upscaling 3.0x. And it also supports FSR 2.0 dynamic resolution scaling. This slide again is the same from the beginning, just as a reminder. This is actually not the whole frame, it's just the part which I cropped out to give you the original size, so it's not compressed. And this is the whole frame, but yeah, due to PowerPoint, it's a bit compressed. But this is native, and then you have quality, balanced, performance, and ultra performance. So you saw they're not completely equal because Cole was breathing and I couldn't stop him breathing, and so he was a bit moving his hand. And also here in this shot, this is ultra performance. You may have noticed that some objects are missing in the background, and also some light bulbs suddenly turned off. And the reason is that the input image, so the low resolution input image, resolution 1280 times 720, actually had not have this objects in, so they were already missing in the input image, and also the light bulbs were off in this in the input color buffer. So that's why, of course, you also can't see these objects in the upscaled one, because the input resource already didn't have them. Performance impact. Please be aware that all performance numbers shown here are based on FSR 2.0 beta version, so they will most likely change for final release. We compared to native 4K TIA sharpener enabled and also ray tracing enabled, because ray tracing is really demanding, so it really makes sense to use upscaling. And yeah, we saw some great performance uplift, especially in ultra performance mode. It's up to 147% what we observed. Summary. We are already at the end of my talk. optimizations, so barriers. I know it's really difficult to get them optimal. Sometimes not even clear what is optimal. But yeah, it really makes sense to spend some time in it because usually there is some room for improvements. Then the right pattern in compute shaders when writing to UAV targets, really try to write in coalesce 256 byte blocks. It can give you a nice performance boost when the target was compressed, when you're working with compressed data. Feature integration. Deathloop was the first title that integrated Fidelity FX Super Resolution 2.0. If you want to know more about this technology, stay on for the next talk. It will be a deep dive for FSR 2.0. We talk about the algorithm, the optimizations we did, and also channel integration guidelines. And yeah, that's everything. And thanks a lot for listening.